Okay, so I was thinking about this. I figured the best place to start is probably a little bit higher level, just to make sure we're on the same page about the overall diagrams and so on. So let me try something wild and crazy. Share the whiteboard. You see that?
Something's happening. Oh yeah, I see a pencil.
All right, let me get out my handy Surface pen since I'm now on a Surface.
Oh, this is very cool.
See how this works. This is totally insane. Okay, so yeah, I think there's like, okay, now let me think about what my boxes are going to mean. So first of all, there's kind of this interface here where, hold on a minute, this thing is in an annoying place. Okay. Over here we have chalk, actually chalk engine. And over here we have, I'm going to call it trait engine. It's kind of a bad name. Maybe the fulfillment context is better. But the idea is we're doing something on the left-hand side in rustc, basically. And like, for example, doing a type check. And when we're doing that type check, we have this data structure, the fulfillment context, that we used to have, where sort of it has two purposes on now. So if we're in chalk mode, what happens is, as we go through the type check, we might find some goal we need to prove, like that some type implements, debug or whatever. And what we'll do is we'll include that in a list. So there's like a list of goals here, goals, and they're just goals that we have yet to prove, basically. And then at any given time, we can go through this list and we'll try to prove them, right? And meanwhile, on the other side, we have the chalk engine, and it's kind of a resident. It has some resident state that it maintains with like incremental state. And the way that it works, its basic interface, is that you can submit to it a goal to prove, and it's going to give you back an iterator, really. So it's kind of lazy. And each time you ask for the next answer, it'll run off and do as much computation as it needs to do to figure out the next answer. And so the idea here is that if you submit a goal twice, what actually happens is inside the chalk engine, we maintain this thing called a table. We maintain sort of one per canonical goal, and that has all the answers we found so far. So if you ask for a goal twice, it'll be very fast to get your answers back, at least up as far as the ones we've computed thus far, because they're cached.
Nico, just to clarify slightly, when you're talking about answers here, I assume you mean basically viable proofs that some type implements some trait or something like that?
Not quite. I mean, a proof must exist. We don't give it back to you directly.
Okay.
What we give back to you is an assignment of the inference variables that is known to be true. For the most part. It might have some region constraints and so on. So if you asked, so as an example, if you asked like, is vec of question mark t implementing debug, we would give you back an answer like, yes, if t is u32. That might be the first answer you get back. And then you might ask, well, what's the next one? And you might get, yes, if t is i32. And of course, there's an infinite stream of answers in that case. So hopefully you won't keep pulling. And we'll come to that in a second. That's relevant here. The way that it works somewhat internally is, we would canonicalize that goal. So it might be like, this might be the vec of question mark 0 implements debug. this might be the table we made for that particular goal, right? And then when we find our first answer, we would add into it like 0 is U32, and then 0 is I32, whatever, as we go through. And we always know how many answers there are. So basically, each of these iterators has like the table index internally, an index to the table and an index to the answer. And as long as it's sort of already populated, it's very cheap. But we're getting a little further into how that works internally now. But my main point is that when you ask it for the next answer, this table, it'll go off and do work. So if it needs, it might say, oh, I have a rule that says, for example, that, well, the rule for vectors is, or one possible value for (0) would be itself to be a vector. So in that case, we might instantiate it as a vec of something, (1), and ask if does vec of (1) implement debug. But when we canonicalize that, that's the same table. So then we'd have like a recursive reference, and that's a chalk can handle that, right? In that case, you would start to go through the answers again. So it would say, okay, yes, the (1) has to be U32, and then you get vec of U32. And so okay, right. So back on the rustc side, we're basically, or actually, there's a little bit of a shim that goes in between the iterator and rustc itself. And what this shim does, this is sort of the chalk shim. I forget where it's implemented. I think it's implemented in the engine itself. And what it does is it tries to, so you don't, rustc doesn't directly interact with that iterator. Rather, rustc asks the shim to compute the answer. And what the shim does is pull answers until it seems like the answer has gotten, until either we run out of answers or we've sort of generalized past the point of utility. So in this particular case, for example, if the question was, does vec of (0) implement debug, the shim would first pull out and get it answer yes if it's U32, and then it might pull and get yes if it's I32, and then we would try to combine those answers into one substitution. And say, oh, well, now we got (0) equals (0). Like there's basically no common ground between these two answers. There's no reason to pull for any more, and we're done. And the engine is optimized around delivering what I've been calling a breadth-first search. It's not literally a breadth-first search. I forget actually if it is or not, but there are various strategies. The main point is it's not depth first. So it tries to give you a variety of answers if they exist, in order to help you reach this consolidation point. So you could imagine it sort of, in a traditional Prolog engine, it might be giving you like ever bigger answers, like vec of U32, before it ever went off to tell you, oh, and by the way, it might not be a vec at all. Right.
I see.
Whereas we won't do that. That doesn't mean we can't take a long time to find an answer. But we are, that's one of my main like things I think we'll want to play with, is this search strategy to try to ensure that we're not getting lost as much as possible. But usually we do a pretty good job. So right. So back to Rust. We'll dig more into the chalk engine, but yeah.
Actually, just to clarify my orientation here. So from the type checking perspective, I guess there are a few different things we might be trying to do. Like sometimes we may just be checking that an already known type implements a trait, in which case the answers are uninteresting. We just want confirmation that the implementation exists. And then other times we are maybe asking both that question, but also there are parts of the type that are unknown. And then we're trying to see basically whether, given that this type has to implement this trait, does the trait system determine that this unknown type must be I32 or something, right? That's right. Basically right?
That's right.
And so
you could get back a variety of answers there, right? You could get back that it must be one specific thing, or that it doesn't matter what it is, but the type implements the trait. Whatever.
Right. Okay, so yeah, because I'm just, the piece that was a little hazy in the description you just gave was like this shim that is actually dealing with the granular answers coming out of chalk. I just want to check my understanding. Basically, what that shim is doing is trying to determine how much information it can get from chalk, whether the information is just, yeah, there's some implementation, but it could be a lot of types, or yes, there is an implementation, and furthermore, it means that this unknown type must in fact be this type over here. Is that right?
Exactly right. It's trying to get as precise a substitution as it can for the inference variables. And so it could, for example, like let's suppose that the values you get back are not U32 and I32, but rather vec of U32 and vec of I32. At that point, it would probably stop, but it would tell you it's a vec of something.
Right. Okay.
Well, no, that's not quite true. It can tell you that, and the way it would do that is it has a way of pushing back into chalk and saying, do you have any answers that invalidate vec of something? That are like you know what possible strands you might pull on that will give you more answers, and those strands could give you an infinite list of answers, but we can still sometimes constrain that they're all vecs of something, for example. So that's how that works. I mean, if it finds all the answers, then it can easily be done. But even if there's an infinite range, we can still sometimes say something, and that's to model. That sort of matches how rustc works today, where we might commit to an impl, but not have fully processed the where clauses, and they might potentially go forever, but because we know there's only one impl and it's for vec of something, that we know something already and we can make progress, right? Okay. If that makes sense. So that's how we handle that case. Anyway, so that if all the types were known to begin with, then the aggregator's job is pretty easy because there's only one possible answer, which is empty substitution. And so it's really a binary question then. Do I get an answer or not a question? Not.
Yep.
Okay. So I'll add one other, while I'm noting concerns. One other concern I have with the current design that I think we can overcome, but it'll take a little tweaking if it becomes a problem, is that I think because of things like size bounds, like it could be very common for us to give back an answer of I don't know. I think that would be by far the most common answer. So if you ask, like, if you have some impl for all t of foo for vec of t, and you ask does (0) implement foo, the answer is going to be I don't know, because we know that it must be a vec of something, but we don't know, without knowing what that something is, we can't tell if that something is sized. If that makes sense. So we can't say yes. But so what we could give back, and I think we will, unless I'm misremembering, is we'll give back I don't know, but whatever it is, (0) has to be a vec of something, right? So that means that the type checker can still make progress and infer that it's a vec of something, but that goal will stay in our list. It's not yet fully proven. And the next time we come in, we'll hopefully have more information about the types, and so we'll end up at a different table because it'll be. Does that make sense?
Yeah.
Okay. So right. So this is the basic architecture, and what I thought I would walk through a little bit is where some of the bits of code are. Let me just say a little bit more about how the chalk engine integrates with Rust, because it's important. When we go off to solve one of these tables, the way that this works internally, I mentioned already, we have this notion of strands. So the table has a list of answers. It also has a list of strands, which are basically kind of like coroutines, so to speak. They're like an answer that we're midway through solving, but we still have some pending work left to do. So it's basically a list of sub-goals you have to solve and some other stuff, and before you found a complete answer. And let's see. Oh yeah. And so when you first create a table, like you'll have no answers, of course, but you'll want to have a lot of strands, and the strands would come from essentially all the impls in the program. Right. That's not exactly true. There's some other sources, but it's kind of what are all the ways I might prove something to be debug, right? Let me put them in my list so I can go eliminate them if they don't apply.
Okay, hold on. So I'm trying to connect this back to my older understanding of chalk. So we used to, back in the old days, there was some notion of like a program that was essentially like the lowering of the trait impulse, and you would ask chalk for answers in reference to that program.
Yeah.
And it sounds like what you're saying here is each time you start looking for answers, or yeah, you start a new table for answers, the first thing you do is dump in the contents of the program as possible proof strands to explore. Is that the right understanding?
That's pretty much right. I think if I remember, I might be misremembering, but based on what I was looking at, let me look real fast. I think the program is at a higher level in the chalk engine. And
okay. Mm-hmm.
it only has, we're going to see it's a callback. Like it's when you instantiate this library, you give it a trait with some callbacks. And one of the callbacks is give me all the program clauses that might be used to prove this goal. Is how it is.
I see. So there's an initial filtering step.
Right. It doesn't really know about traits per se, right? But it just knows it has a goal to prove.
Yeah.
But and your job is to give some superset of the applicable clauses.
Mm-hmm.
And actually, it doesn't matter. You could give all clauses that exist, and it'll find a job. It'll be less efficient because it's not very good at, it'll search them one by one. The hope would be that you will take you'll take as much information from the goal as you can to narrow that down. So like at minimum, you might look at the trait, but you might also look at the type and say, I already know it's a vector. Like I've hashed my impulse by the self type. That's what we do in rustc today.
Mm-hmm.
Like not the full self type, but a little bit of the self type, just enough to like narrow it down to use it. And you might do that.
Gotcha. Okay.
So I have a question. So I don't know if you said this, but how is the chalk engine interfacing with type inference today? If we get t equals u32, are we feeding that into the inference context, unifying that, or?
Yes, we will do that, and I'll talk about that. But yeah, we will.
And to what extent does that like replace existing type inference logic? Kind of the other question.
I mean, it plays the same role as the trait code in rustc today. So there's in the rustc side, there's somewhere an inference context, which is, so when you're doing type checking, you sort of have a trait engine, and you have an inference context, and you're gonna come up with something you need to prove, and you're gonna take some goal like, well, this has been our example, so I'll just keep using it. Let's call it $32 is debug, right? And that's $32, of course, refers into the tables here. And we're going to submit this goal to the trait engine, which I think we also give it a reference to the inference context when we do that. And it's going to go and canonicalize that and turn that into, like, ask chalk to deal with it. Chalk doesn't know anything about my inference context. It's because we've canonicalized it. We've taken all the inference variables and given them sort of pulled them out and given them a renumbering, sent it off. And then chalk will give us back an answer, and we'll sort of translate that answer back into the inference context and do the unification. So as part of processing that goal, we might figure out that $32 is uint, right? And we would tell the inference context, oh, hey, unify $32 and uint. And that, in the way that happens, well, that can happen. Yeah, no, that's just right. So basically what happens is that the iterator, the aggregator, this iterator aggregator thing here will, I think you can see my cursor probably.
Yeah.
Will give back a substitution, right? So it says, oh, the zero, what you called, because it gets back it's been given this request that has the canonical number, and it'll give back a substitution like 0 is u32. I know that, and then the trait engine will say, okay, well, 0 was $32 initially. That was the name the original name we had for it. So let me unify those two things. And that's how we get this, if that makes sense.
And that only works for like certainty, not like a list of possible values.
Right, it has to be something you know for sure, but we don't have to know that, like I said, you don't have to actually know that the whole thing is proven. You only have to know that the only way to prove it would be, so we might still not know whether, well, in this case, because the full type is known, we would just know the answer. But this could be a substitution that itself includes more variables, and without knowing the value of those variables, we don't know yet if the full result is done.
One last point on that. So I know that there are sometimes ways of proving, if there can be more than one way to prove a given goal, and that would give you a different unification, right?
Mm-hmm.
How do we prevent like the wrong unification from getting stuck in the inference context? Yeah,
so that's the role of this aggregator actually, its job is to pull enough answers until either we've seen all the answers, so we know when we're done basically, and if we've seen all the answers, then that's good. But there are basically three possible outcomes. We've seen all the answers, or we've I guess just two, or we've generalized the result to something that none of the possible future answers would invalidate. And the simplest way to do that is you've generalized it all the way to I learned nothing, right? In that case, like, or rather like, that's how much I learned nothing. Yeah, I guess I learned nothing. So (0) could be any type. In that case, whatever future answer we come up with will clearly not invalidate that. But sometimes we might have learned more. And the way that and that's where I was saying earlier to Aaron that we sort of push back as we go, we're like saying for the answers we've seen so far, they had these parts in common and these parts were different. And then we push that down and we say, okay, look at the answers you've got coming up. Do any of them potentially potentially invalidate that? In that case, if the answer is no, then I can just sort of stop. I don't need to pull the rest of those answers because they're not gonna add any new information. So yeah, and I think yes. Okay, so this is the chalk engine itself. I guess I'll do a little bit more context since we're here. I was just going to say that it's pretty generic. It knows. It's really just the logic of like managing these tables and strands. So it doesn't know. It's kind of got some context. We'll see later that has like a bunch of associated types for everything from like what is a goal, what is an environment, what is a type, all that stuff. It does require some amount of, it does bake in a few notions that are Rust specific, like type, but it's pretty minimal. And even type is really just, it just sort of says, it'll have some callbacks like, hey, unify these two types, tell me what happened. But I don't need to know what they're like made up of. So, okay. All right. Any more questions on the big picture? I think that's the whole picture.
So one, this is maybe not super relevant, but just as a reminder, so we have an inference context, and then we have fulfillment context that refer back to it. When do we create new fulfillment contexts? Like, what's the sort of life cycle?
Well, you can create them sort of anytime, but it's basically one per function.
Okay.
I think sometimes we might create sub-fulfillment contexts within a function, and that's okay.
Okay.
They're really just a list of things we have to prove. They're not really any other state. So
yeah. Okay. So it sounds like from the perspective of chalk integration and so on, we can just focus on the fulfillment context. And like relationship back to the inference context is not that interesting.
Yeah, and in particular, there's a one-to-many relationship. I guess that's the important part. They're like, they all share the same inference context, but they you can have many fulfillment contexts. That's it's sort of okay. The only problem is like, if you're just seeing whether something could be proven, but you don't, it has side effects on the inference context that it's associated with. So if that's not something that has to be true, then it wouldn't be true that question mark 32 must be uint or whatever. You know, like, in other words, you have to manage the side effects. But as long as they're all things that have to be true, it's fine.
Okay.
Just to clarify, is there one chalk engine per fulfillment context or per inference context?
No, there's one chalk engine for the whole compilation.
Okay.
So that's a big point, is that anybody that has to prove that a vector is debug goes to the same table, no matter what function they're working under. The only sort of problem, or the only difficulty, is I didn't show it, but part of this goal is also the environment. So it's also the where clauses that are in scope, roughly speaking. However, in my measurements, I found that 99% of the things would be cache hits. So this should still be pretty good.
Cool.
Something like that. I think it was 99. It was certainly starting with a 9 and a big number. But
where clauses in scope are expressed with like a implication goal, right?
More or less, yeah.
More or less.
So they too are canonicalized and so forth. Okay. We actually do distinguish the environment from my implication goal, but they're not really solving an implication goal just moves something into the environment, essentially.
Right.
So it's not really a real difference.
One other small question. It was a little unclear where exactly the canonicalization happens. Does it happen on the trait engine side, in the aggregator, or in chalk engine itself?
It happens at the trait engine side right here.
Okay.
So
when you add it as a goal.
It's going to select a goal which is stored in uncanonical form.
Okay.
It's going to canonicalize it and then send it over.
Got it.
And then get back a response in terms of those canonical variables and translate it back. And part of the reason it's stored in uncanonical form is that, well, that way, if there are other side effects that wind up unifying those variables, like maybe we know we had to prove vec of question mark 32 was debug, that doesn't tell us what question mark 32 is, but some other part of the program does, then later, you know, when we canonicalize, we'll see that question mark 32 has been unified, and it'll get canonicalized differently this time, and it'll get canonicalized to the actual type.
Gotcha. Okay.
And which of these interfaces are Rusty queries?
There's a query that takes a canonical goal. Basically, the query is like here.
Okay.
Diagram's getting kind of messy, but yeah, the query takes the goal and gives back the answer, essentially.
Yep.
I guess it's like here because
between the engine and or the chalk engine and the rest.
Yep. It gives back the substitution that resulted. All right, so
okay, the aggregator. Okay.
All right, let's see. Let me show you a few bits of this code. I don't know what's going to happen if let's find out. If I don't close this whiteboard, I'll save it for one thing. Okay, just in case. Do share. Let's see. Do you see a really tiny font and a bunch of code?
Yep.
Shall I make it a little bigger? Let's see if I'm actually able to do that. I forgot that I don't. Oh, no, it did work. Okay. But I switched terminals since the last time I tried this, because the last time I remember I was like pressed all the keys I could think of, and none of them were making the font bigger. So, okay, what am I looking at? I don't even know. Oh, I'm like in chalk code for something. Right, so let's start with this. So I said trait engine in my little chart, and that was like the fulfillment context.
Mm-hmm.
There's actually a trait in rustc called trait engine, and it has these operations like normalizing things, registering something, a predicate that has to be proven true. And select all or error means try to prove all the things. And if you fail, that's an error that you can report. Hence, you get back this error. And select where possible means try to prove all the things. Oh, I see. The only difference is select all or error will give an error if there are things that can't be proven. Whereas select where possible just leaves them in the list for later. It's only an error if they were proven to be false, essentially. And yeah, so this is basically the interface that the type checker needs from the fulfillment context. And we introduced this little shim so that you can write -c-chalk and stuff. So like the old school fulfillment context with Rust's current trait solver also implements the same trait, right? This is the old school one. But the newer one is here under chalk-fulfill.rs. And I'll start with this select where possible, because this is that algorithm I talked about. So you see that it maintains a list of obligations that have to be proven, which we iterate through. Here's where we do the canonicalization. So we're going to canonicalize the query. That's going to give us a canonical goal here. And then this is, you asked Tyler, T. Mandry, what is it? Yes, okay.
Tyler.
You and Taylor confuse me. Especially now that you're both at Google, it's like, oh.
Yeah.
Right. So this is where the actual query comes in from Rusty's perspective. This evaluate goal, and here's the actual query definition. We'll come back to that. But you see, we're giving it the canonical goal, and we're getting back a response. And this response is, it's a result. It's a canonical query response. The no solution means there was we knew that this is false. Otherwise, we get back this, maybe it's true or maybe it's not yet fully proven, and we can ask, like, is it true? Is it fully proven? If so, we're making progress. And we don't have to, this instantiate query response and region obligations. What this does, oh, that's actually interesting. Okay, that's a fix me, but we'll come to that. What this does is take the substitution that came back and unify it into the inference context, unifying the inference variables. And here we say, if it wasn't proven, we'll just leave it in our list for later. We'll come back to it. This is a bit of a bug. Like, I think we should be instantiating the query response and region obligations in both cases, potentially. But in other words, this is like that case I mentioned where it might be that we know something about the variables, but we don't yet know that it's fully proven. I'm not sure why we're not doing it in both cases. Maybe it's just an oversight, or maybe there's some more refactoring that's needed. But that's the idea. So far, so good. Okay. So if we go dig into evaluate goal, that's over here. Let's bring that over. This is the actual code. So what it does, there's a bit of a thing. Where does this happen? Right. Actually, before we get here, let me jump back to the old code. I wanted to look at the register predicate obligation, because this is actually interesting. So this is where the type checker says, hey, we have something we need to prove. And a predicate obligation is the old Rust-C notion of things to prove. So it's all very Rust specific. This is a predicate. It's like, whatever. Some trait holds, some outlives relationship, a type relationship, and so on. And what we do is we call this method in environment. And that is going to translate, or it's a function rather, but we call this function in environment. And it's going to translate from the Rust-C notion of a predicate into the chalk notion. And we sort of have like, we thought we might keep these more unified, but we wound up kind of separating them. So Rust-C has sort of two notions of things. There's like the old one and the new one. And so, so one of the things that this does, this predicate obligation includes a parameter environment, which is the set of things the where clauses in scope, basically. And those are represented quite differently in rustc and in chalk. So this is like a little bit hacky right now. If we're in chalk mode, we keep a def ID, which was like what function did this parameter come from? And then we can construct the chalk environment from that def ID. If you see what I mean. So we sort of have these two parallel things going on. So there's some translation that takes place here. It will be nice to refactor that at some point. I don't exactly remember why we had to do that, but so this is because the chalk notion of an environment is quite different and included stuff like implied bounds and so on that just aren't part of the rustc's notion. But so we'll do this translation. We'll call this evaluate goal. Let's take a look at evaluate goal again. Evaluate goal. Oh, I'm trying to remember where this happens. It's confusing to me. Let's see if I can find it. Where is it? Oh, there it is. Right, right. So the first thing evaluate goal does, we already converted the environment from the rustc notion of an environment to the chalk, to the sort of chalk version. We also have to convert the goal. That's what evaluate goal does here. It's saying, oh, so predicates was the chalk, the rustc notion, but the chalk version is called goal. This is a little confusing. I'm not sure I have the right terminology for this. When I'm saying chalk here, what I mean is there are a set of types that are in rustc that represent the chalkified versions of traits and so forth, right? But they're not in chalk. They're rather when you instantiate the chalk engine and we have to set its associated types for like what is a goal and so forth. This is what these types are.
Mm-hmm. And is this, just to clarify, Nico, I think you mentioned in the working group meeting that like right now the lowering code in chalk is not used in the rustc integration, and you'd like to factor that out?
Yeah, they both share that code. They both have their own copy of that code.
No, but okay, right. Because this feels like what's being enumerated here is the lowered form of these goals. And
yes.
So like the plan is ultimately that rustc would not have this, would be operating purely at a higher level,
right?
Like Rust specific thing, and then this would be in some shared library.
That's what I would like, yes. But it's a little tricky because it references types and so forth, for example.
Right.
So
okay.
Quite, yes. So, right. So this code is right now just in traits, the librustc/traits. That's where I am here. You can see up here on this line.
Yep.
And it has, it might look familiar if you've looked at chalk. So it has like a domain goal with various options. We can get into the details later, and then these are like the meta things, right? So this is A implies B, A and B are both true, not A, and so on.
Yep.
Oopsie, wrong key. So, right. So we convert into these format, and there's one thing I wanted to highlight. There's some special cases here for some reason or another that I don't remember. But then the general case, we invoke this lower method. And this is exactly the lowering code you were talking about, Aaron.
Okay.
It lives in the librustc traits. Notice the underscore. This is a different crate. A subtle convention. In general, the rustc : traits code is like the shims that are needed to bridge into like the query, let's put it, the signatures and the query interface code, and the query implementations live in the rustc _traits crate.
Okay.
Except for all the old rustc trait solving code, which all lives in librustc. But when it's the newer stock code. And that, I don't know. Anyway, Sunjay told me that division was helpful. I still think it's a little confusing. So this lowering, right? There's this trait called lower. This is basically like what it says here, lowering from a rustc construct into a chalk-like type. And it can do a couple of different kinds of lowering. One interesting thing is that lowering into a goal, something to be proven, is sometimes slightly different from lowering into a clause, something you know is true. So you can implement it twice if necessary. But for example, here we say, okay, lower from a predicate into a goal. I don't know, it does some stuff. It's not too exciting. That's just a dispatching impl, obviously. But so now here, at this point, the point is we now have a chalk-like lowered goal. And actually, this is quite inefficient. So that picture I showed you is wrong, as presently implemented. I told you that we have a persistent forest that lives across, a persistent chalk-like engine. And but we don't. I forgot. We're actually making a new forest for every query. That's totally inefficient. There's nothing wrong with it. It's just going to avoid all the caching benefits. The plan is I don't think there's any good reason for this to be this way. It's easier. So yeah, forest is the name from the chalk engine crate for like well, I don't know why it's called a forest. I guess I called it that. I guess I thought there were trees. But really, there's a DAG. But anyway, for the set of tables
Okay.
and their relationships to one another. So maybe that name is from an older solver or something. In any case, so it calls forest.solve. That'll do this aggregator thing. I'll create the iterator, do the aggregation, come up with a substitution, and then we map that back to the answer that we put back as the result of the query. So we are creating a new forest. We're not going to get as much caching as you would like. However, we're still getting caching, interestingly, at the level of the rustc query itself, right? So what that means is, the difference is, like, if I ask you if lots of people ask about a vec of $t equals goal, they will all get the same response. But if somebody asks about something which, as a subtask, has to solve that, it will redo that work. Whereas if they shared the forest, it wouldn't redo the work at all.
Right. And yeah, in other words, like once you're off to the chalk engine, you're not using the rustc query system. There's no sort of re-entrancy in that sense.
That's right. You never come back out. It has its own. Well, you do, but not to this query.
Okay.
Which is what we're going to talk about right now. So,
nice.
Yeah. So that's kind of, now we've seen the forest. I guess the last interesting thing that I noticed, but I'd forgotten about, that we've all talked about lazy normalization. If you compare this is the two implementations of trait engine. Oopsie, where am my cursor? There it is. This is the old one on the right-hand side. You see that normalized projection type does a bunch of work figuring out what an associated type is and so on. But on the chalk side, it doesn't do anything, because it's lazy. And this normalization will take place. The chalk engine will handle it. So that's kind of neat. So let's look at this integration now. So maybe I'll stop for 1 second from looking at rustc and just go over to look at chalk engine. So the chalk engine code has a bunch. This context.rs. This is all the traits. You see, there's actually kind of a lot of stuff that you have to implement to use this, and mostly there's a whole bunch of types, but there's also some operations on those types, and that's what I wanted to show you. So some of them are really simple, like goal in environment. This kind of says, given an environment and a goal, give me a goal, glue them together and give me the aggregated. Like maybe if we had, like, I don't know, GATs or something, we could express some of these things a little more nicely, but.
Got a bootstrap.
Right, exactly. So then it has some questions like, is this a co-inductive goal or not? The thing I wanted to show you was scrolling down a little bit. First off, where is it? Here. This hook, program clauses, this is the one that says, given this environment and this goal, you give me back all the ways, a superset of things I might use to prove it.
Yep. So that's where the strands originate.
Right. And jumping back up a little bit, I think, or no, jumping back down, sorry. Here we go. Yeah, this one, another key callback. Most of these are not that interesting. These are like the most important ones. Unify parameters. This is where we're saying, here are two things, make them equal. You'll note we have a variance in there. I'll come back to that in a second. Normally that's not used because traits normally are just require strict equality, but we have subgoals like subtype. I don't know. Anyway, I'm not sure I like how that's handled, but it's okay for now. So it says take two parameters and unify them, and give me back if that's true or false or whatever. And because of lazy normalization, so what can happen here is that this can succeed, but give back region constraints. So like if you have ampersand tick A and tick B, it might say, oh, but only if tick A equals tick B. But it can also succeed with normalization constraints. So it can say, if you had a projection on one side and something on the other, it would say yes, but it would give you back a new subgoal you have to prove. So really this unification is not special. I think it's kind of just another goal. Like that's kind of true for any goal, but it's one that we handle a little specially. But I feel like it kind of helped me to think about it eventually as there's a notion of unification that is like of equality that is built into the logic somehow, that like they're textually equal or something. But what we're really saying is whenever we have to equate two types, we sort of have to prove a subgoal, equate T1 and T2, and that may require doing some extra steps. Yeah. But we treat them a little differently in that normally we sort of, and maybe this is not, I don't know if this is actually right, but this is how it's happening now. Normally we would process subgoals kind of, they would make new tables and go down, whereas this one says, does all the work and then gives you back a list of things to prove. Sort of a little, anyway, it doesn't matter. That's too in the weeds. The point is, this is the main hook you have to implement. Unification and the program clauses. And there's a few other variants of unification. These things are, they're unifications, but in a specific context. I won't go into it. So if we come back to chalk context, now we're looking back at rustc. We can kind of see some of these hooks. So the program clauses, wait a minute, oopsie. Program clauses goes over to this function for some reason, which, yeah, and what it tries to do is it tries to say, okay, if we need to prove that some trait is implemented, if you just look at, there's a document on the rustc guide that sort of shows you all the chalk lowering rules. You can kind of fairly easily see where could such a rule come from. It could come from lowering the trait, or it could come from lowering some impulse. So from impulse, sorry, I guess it can come from implementations of the trait. And I think, right, this has to do with implied bounds. Let's just ignore that one for a second. But the point is you can kind of go down and see what are the Rust language constructs that could be lowered into a rule that would satisfy this goal. And then our job in this code is to go pull on those. And this ties in with IDEs and on-demand processing, because ideally, also with specialization as it happens, ideally we would only pull on like a sort of minimal set of things. We could go get all the impulse for all the traits, but it would be inefficient. And if there's type errors in those impulse and stuff, we might get weird results. But if we can, the more we can narrow this set, the faster you'll be able to get answers back from the RLS and so on, right? And it also ties into specialization and becomes significant to the language definition in that, when you have to recursively, if figuring out whether one impl specializes another requires solving predicates, then the set of things we pull from here could create a cycle that would error out if it's too broad. So we should put this. This is like a significant callback for the language semantics. Anyway, I think right now what it does, assemble clauses for impl, basically just iterates through the impls for the trait. I don't exactly remember. I have to go. I was looking into this and didn't quite get done figuring out the stuff with implied bounds, the interaction there, but we'll come back to it. But this part is significant. So there are some things. This is getting to the work that is actually in one of the sprint goals now. Sometimes we don't have explicit impls, right? We have things that are built into the compiler. So sized is an example. And so it's our job here to sort of add those rules, right, as needed. And one of the challenges is sometimes in order to figure out what the rule would be, you might like to know a little bit about the type in question. So if you look at like sized, if you think about sized, it's easy to tell you if a Boolean is sized. It's pretty easy to tell you if an array is sized because it's like sized if the argument, I guess arrays are always, I don't know, whatever. It's sometimes easy to tell you like in terms of other types if something is sized, but it's pretty hard to tell you if some random inference variable is sized, right? The set of rules that you would need to properly model this, the rules we would want, would basically enumerate all the sized types as answers, right? Which is a lot. And we could do that, but this is something we want to figure out a better answer to. I think it will also be very important. I mentioned long ago, we want to prevent the solver from getting stuck and trying to decide if this is too much of a digression, but basically, stop me if you feel I'm going off and losing you. To jump back to the chalk engine a little bit, you had those tables, and the way that the chalk engine kind of works internally is it has a list of things to prove. It's going to pick one to focus on and pull answers out of it, and then it's going to sort of feed those answers in. So if you had to prove, let's say you have two goals, T is debug and T is display or something. You might start with the debug and find, well, what are the values of T that make it debug? Maybe it has inference variables in it. And for each of those concrete answers now, you can go take them off and see if they're display. So the first goal acts as like a producer, and the other goals act as like filters. Does that make sense?
Can you say that again? You lost me.
It's probably too detailed. Let's just say, I'll come back to it when I'm not as deep into the Rust C code. I'll just say, suffice to say that the order in which we solve goals is very important. And we would prefer to solve goals that have more types, like fewer answers first. So something like $T : sized is like the worst goal. We never want to solve that goal, right? We always want to solve some other goal first and come back to that one later. And ideally when we know something about T.
Okay, let me ask a couple of clarifying questions here. So one thing I'm getting a bit confused about is the callback we were looking at was essentially the lowering, like the creation of strands, right? And so one question I have is there, like we are treating answer generation lazily, but it seems like we are treating strand generation eagerly. Is there a simple reason that we do it that way? Do you see what I mean?
I do. I'm trying to decide what I think. it seems like well, for one thing, we do need the ability, in order to know when we can stop pulling on answers, we do have to have, I mentioned that sometimes we'll take back a partial answer and walk over the set of pending strands to see if any of them invalidated. That would be hard to do without a list of them. However, we don't always need to do that. I suspect we could be lazier. I think it's important that we generate the strands in a kind of deterministic order and so on. I'm not sure how important that is, but I think if we're not careful, and honestly, that's neither here nor there, of course. I mean, we could be deterministic and lazy. So yeah, I think we could be lazier. I don't know if it would solve any fundamental problems, but I think we could be lazier.
Okay. Well, I guess, I mean, the other thing I was wondering is like, you were sort of initially talking about, okay, when we're generating these strands, we have some cases like sized that potentially involve a lot of strands, I think. But you sort of switched to talking about the order in which we try to solve goals. And that I got a bit confused because again, the strands seemed like we were eagerly producing these things and eagerly producing the set of all, sized things seems problematic. You see what I mean? Like I'm a bit confused exactly.
Yes, I see your point. So yeah, so it's definitely, there's sort of two problems. I mean, it's definitely true that producing the set of all size strands would be a lot. It's not infinite because they can be recursive. It would be like 1 per struct or something, but still not good. The reason I think it would be, maybe I do have to explain. To answer this question, maybe the best thing is to jump a little bit back to the chalk engine. Or why I shifted goals is, I guess I'll put it like this, because the reason I shifted is that the order in which we select the goals has a lot to do with which things, when we end up in this callback. If we select in a different order, we can avoid annoying questions a lot of the time.
Yeah, I see. Okay, so I guess another part of this is, okay, I think I hadn't quite put all these pieces together in my head. Like in the old model of chalk I was thinking about, you basically had a preliminary lowering step, which gave you the entire contents of the program basically at once, and then you could just query on that. Here, like, there is a laziness already in the sense that you're only doing that lowering based on goals that you're trying to prove. So the only time you would ever start enumerating every sized type is if you actually encountered a goal that was just $t : sized. And I think what you're saying is we want to avoid, we want to sort of put off those goals as much as possible to avoid that enumeration.
Yeah, and what we actually do is probably not bad. Like we want to put them off, that's right. The only thing I would say is we do have to have a strategy. Like we can't always put it off.
Right.
So we need some answer. What we're actually doing here is maybe good. It might even be the right answer. Where is it? Well, I don't know where it is, but it comes down to that the chalk engine. Oh, I guess I'm gonna have to go soon. But the chalk engine answer it can be. Give me 1 second. It doesn't have to be yes or no. It can also include I don't know, essentially. And I think we're currently giving back an answer of this kind. It's like do not prove, or cannot prove is how we would call it. But the thing is, it's a little bit sketchy because like there are answers. So it's kind of wrong to say the only answer is a cannot prove answer. That's not really true.
But I guess.
But I think it probably doesn't hurt anybody for.
Right, because I mean, this is basically only going to happen when we have some inference variables floating around. I mean, basically, this is just affecting how the lengths we go for type inference, right?
Yeah, I think so. I think there are fancier caching strategies that we're not using where it would cause problems. So there's stuff like subsumption caching, where the idea is like, let's say you've got a goal like vec of (t is debug, and you go and solve it, and then you have a later goal that's like vec of u32 is debug. In the chalk strategy, those are different tables. They're not going to share work. But there are other strategies where you try to say, oh well, this is a subset of that other question, so why don't I just use the results from that and filter them out, basically. But that would not work if you did that with size under this strategy, right? Because size doesn't have all the answers. And so I'm just a little nervous. I think it's fine, but we are sort of breaking the the model a little bit of the solver this way, and so I would like to. We should keep our eyes out for where it might lead us into bad assumptions. But I think, yeah, I think that we're probably going to wind up with some sort of thing that lets it bail out when there's just a clearly pointless task. But we're going to try to order our clauses so that we try not to get there in the first place, if we can at all possible.
Interesting.
And maybe we can make that bailout a little more...
like first class.
Yeah, exactly, or fine-grained or something, so that that's... All right, I have to run to another thing. But I think we kind of almost covered all the things I wanted to cover, so that's good. We need to narrow in exactly on, I think, a good starting point for what the task is. I realized as we were talking that what I thought the task should be isn't, I don't know, maybe it wasn't right. But like one obvious starting task might be to do one of these fix-me's, which is to say, rather than trying to solve some fundamental like refactoring of how we select clauses or whatever, we should start by, let's just copy some of the existing code just to get a feel for what's happening and learn the system. So in particular, maybe implementing we have the built-in impulse for sized. Maybe we should try to make the built-in impulse for copy or something. And I'm sure that will come, once that's done, then we can talk about how to refactor the code around it. But makes sense.
Yeah. Well, it sounds like we should sync up when you have time and get this a little crisper. But
yeah,
this overview made a lot of sense.
Cool. Thanks. Cool. Talk to you later.
Thanks, Nico.
Thanks. Bye.